Okay, let's dive right into this explainer. We walk past massive concrete pillars every single day, completely taking for granted the incredible amounts of energy and weight they're holding back. But when those invisible, silent forces are miscalculated or overwhelmed, the results are terrifying. They don't just crack, they collapse with absolute devastation.
When we get up close to these failures, we're seeing the absolute worst-case scenario. Thick steel rebar gets completely mangled, literally peeled back like cheap wire, while solid concrete is pulverized into dust and rubble under immense, unforgiving weight. This isn't just property damage, folks. Sudden, catastrophic structural failure is an area where engineering mathematics becomes a literal matter of life and death. Welcome to our explainer on the mechanics of materials. Today, we're going to unpack the fascinating math, physics, and engineering that prevents the buildings, bridges, and parking garages around us from, well, collapsing on our heads. We're focusing specifically on compression members, better known to most of us as columns. So here is our game plan for breaking this complex topic down. We'll start with the anatomy of failure, compare crushing to buckling, explore Euler's ideal buckling theory, discuss the importance of supports, and finally, deal with the messy reality of real-world imperfections. Section 1, the anatomy of failure. First things first, we really need to understand what a column actually does within the structural skeleton of a building, because it's definitely not just decorative. In engineering terms, a column is just a vertical member carrying a compressive axial load. That's really just a fancy way of saying weight pushes straight down on it. Now, that downward load can happen in two main ways. First, you have an axially loaded column, where the weight is perfectly centered over the centroid of the column. But then you have an eccentric column, where the load is offset by a tiny bit, a specific distance we call the eccentric distance. And man, as we'll see later, that tiny offset changes the physics entirely. Moving right along to Section 2, crushing versus buckling. How does a column's physical shape, specifically its height versus its thickness, dictate how it's ultimately going to fail? It really is a tale of two very different columns. Think of it like this. If you take a short, thick rubber eraser and press down on it with your hand as hard as you can, it just squishes and bulges out, right? That's crushing. Short columns have a huge cross-section compared to their height, and they fail simply because the material itself just gives up. But if you take a long, flimsy plastic ruler and push down on the ends, it immediately bows outward in the middle. That outward bending is called buckling, and it's exactly what happens to long, slender columns. When a short column crushes, the sheer destruction is incredible, even if the column wasn't overly tall. If the compressive load is too great, it's game over. The raw material itself, the concrete and the steel, literally yields and crushes under the immense pressure, causing the entire column to pancake right in on itself. But for those long, slender columns, the failure mechanism is a totally different beast: lateral deflection. The exact second the column hits a very specific weight limit, known as its critical buckling load, it suddenly becomes mathematically unstable. It just bows out to the side. The material itself might be perfectly fine, totally strong enough to hold the weight, but the slender geometry causes it to whip outward and fail. Section 3, Euler's buckling theory. To predict exactly when that terrifying lateral bending happens, modern engineers actually rely on a formula developed all the way back in 1757 by the legendary Swiss mathematician Leonhard Euler. Here's the catch, though. To use Euler's beautiful theory, we kind of have to pretend we live in an impossible, perfect universe. His math only works for an ideal column. That requires 4 massive assumptions. The column must be perfectly straight before any weight is applied. It must be made of perfectly consistent, homogeneous material. The load must be perfectly dead center on the centroid, and absolutely zero horizontal wind or lateral loads can push against the side. Assuming all those perfect conditions, we get this incredibly elegant equation for critical stress. The absolute crucial part in this equation is the L over R on the bottom, known as the slenderness ratio. L is the length, and R is the radius of gyration. This ratio acts as the ultimate measurement of the column's flexibility. Because it's squared and sits right there in the denominator, it means the more slender and flexible a column is, the drastically lower its critical buckling stress becomes. It drops off a cliff. But Euler's brilliant formula has a huge limitation in the real world. When we map out the data for structural steel, the theory only works up to a certain point. For a specific steel with a yield stress of 250 megapascals, if the slenderness ratio drops below 89, the trendline just hits a brick wall. Why? Because below that ratio of 89, the column is short and thick enough that the steel yields and crushes before it ever even has a chance to buckle. If you try using Euler's formula on a short column, your math isn't just slightly off, it's dangerously wrong.
Section 4, the importance of supports. So, we know length matters, but it's actually not just physical height. The vital importance of how a column is fastened to the building changes absolutely everything. The way support conditions alter what engineers call the effective length, or Li, is wild. If a column is fixed rigidly at both the top and the bottom, its effective length is literally cut in half. It forces the column into this rigid S shape, making it mathematically twice as strong against buckling compared to a simple pinned column. On the flip side, if a column is fixed at the base but completely free at the top, think of a flagpole, it sways easily. Its effective length becomes 2L, meaning it acts as if it's double its actual height, which makes it highly susceptible to buckling. And this brings us to a massive plot twist in our engineering story. We've spent this whole time living in Euler's perfect world. But what if the column isn't perfectly straight to begin with? Section 5, real-world imperfections. Let's dive into the messy, realistic reality of construction. Because as anyone who has ever visited a job site knows, manufactured materials always have flaws. In reality, columns almost never suddenly buckle out of nowhere in a split second, like Euler's theory suggests. Concrete has air bubbles, steel has slight variations, and loads are virtually never perfectly centered. Because real-world loads are slightly offset, creating that eccentric distance we talked about earlier, columns actually start bending slightly the very moment any weight is applied. To handle this, engineers pivot to what's called the CEng formula. This allows them to calculate the stress by factoring in that exact offset distance, ensuring the column doesn't slowly bow past its allowable deflection limits. Because of all these unpredictable imperfections, the microscopic bends, the slightly off-center weights, a random gust of wind, engineers can never rely purely on the theoretical critical buckling load. No way. They have to divide that critical load by a factor of safety. This gives them the allowable load. So if Euler's math says a column will buckle at 100,000 pounds, an engineer might apply a factor of safety of 3, meaning they will absolutely never allow more than 33,000 pounds on it in the real world. That built-in buffer is exactly what keeps us safe. And that is the incredible reality of our built environment. It's not magic, and it's definitely not perfect. Every building you enter is held up by the mathematics of managed imperfections. It's the rigorous application of physics, the deep understanding of when materials crush versus when they buckle, and the incredibly wise calculation of safety margins. So next time you walk into a massive, multi-level parking garage or stand in the towering lobby of a skyscraper, take a good look at the concrete columns around you. Ask yourself, just how large was the factor of safety the engineers used on that column, standing right next to you? Thanks for joining me on this explainer. Keep your eyes open and keep questioning how the world around you actually works.